Okay, for this section, we're doing geometric distributions. So you're going to try and find the probability of geometric distributions, the mean and standard deviation, and we're going to try and distinguish what's the difference between binomial and geometric distributions. So consider the following distributions. The number of coin flips it takes to get heads. The number of children a family has until they have a boy. The number of free throw attempts it takes for you to make a shot, or the number of free throws attempts it takes for you to miss a shot. How many times you have to roll to get a 5. And if you notice that all of these situations, these are all geometric distributions. In simple terms, these are all situations that involve counting the number of trials before a specific event occurs. So in binomial distributions, we did fixed number of observations. Well, if you look at all 5 of these situations, there is no fixed number of observations. We have the number of trials. How many times does it take until I flip a coin and get heads? So it's not how many children, they don't give you a set number of children, they don't give you a set number of coin flips, they don't give you a set number of free throws. We're now counting how many times until I succeed. So a random variable x is geometric if it meets these 4 conditions. If you notice, the first 3 conditions are the same as the binomial distribution. We still need success or failure. We still need independence. Are all observations independent of each other? And is the probability of success the same for each observation? The last one is different though. The variable interest is the number of trials required to reach the first success. How many? I'm counting the trials until success. Whereas for a binomial, we had a fixed number of observations. We don't have a fixed number of observations anymore for these distributions. So here's the geometric probability formula. I'm going to try and use words to help you remember this formula. Unfortunately, this is not in the reference sheet for the AP exam. So let's try and see how we can remember this formula. If x has a geometric distribution with a probability of p success, so whenever you see p, that's talking about the probability of succeeding, whatever the success is for the x random variable. And whenever I'm talking about the probability of failure, I'm talking about 1 minus p. 1 minus p is the probability of failure, p is probability of succeeding. On each observation, then x can take on values 1, 2, 3 with no upper limit. That means it keeps going. So the probability that the first success occurs on the nth trial is the probability of failure, 1 minus p, to the n minus 1. So how many times did you fail until you succeeded? That's what I'm looking for in geometric probabilities or geometric distributions. So we're flipping a fair 2-sided coin. What is the probability that the first head occurs on the 5th flip? Well, I have first I have to figure out what the probability is. And for a coin, I have 2 options. It's either heads or tails. So the probability of getting heads is my success, 0.5. Well, what's the probability of failure? What's 1 minus p? 1 minus 0.5 is 0.5. So the formula is the probability that x is equal to n. N is the number of trials, or how many times did I flip the coin. And here it says 5, 5th flip. So 5 times I flip the coin. So here it's x equals 5 equals 1 minus p to the n minus 1 power times p. So I failed 4 times. I didn't get heads on the first 4 times because it says on the 5th time I got heads. So 0.5 is still the probability of not getting heads or getting tails. And I got that 4 times. And then the last time on the 5th try, I got heads. I multiply those together. And I get 0.03125. Let's try the next one. where the probability for success and failure is not the same. So I'm rolling a single fair six-sided die. What is the probability that the first 5 occurs on the second roll? The probability of failure here, 1 minus p, is not getting a 5. Well, on a single six fair-sided die, I have options 1, 2, 3, 4, 5, and 6. And the probability of not getting a 5, success is 5. Not getting a 5 is going to be 5 out of 6. There's 1, 2, 3, 4, 5 options out of 6. And the probability of succeeding is 1 out of 6. Now, remember the formula is x equals n. Well, n is second roll. How many times did we roll? We rolled it 2 times. And then our probability for this is how many times did we fail? Well, the first time I didn't get a 5. So that's to the first power. And then the second time I did get a 5. And then the answer, or the probability for when 5 occurs on the second roll, is 0.1389. On the calculator, there is geometric PDF and geometric CDF, but I'm not going to teach it to you. It's confusing. It's different from binomial CDF and PDF. So we just did on the last slide geometric distributions without having to use fancy calculator functions. So I'm not going to teach it to you. And geometric distributions are so easy, so we're not going to use the calculator for these. Mean and standard deviation for a geometric distribution. Again, I'm sorry. These formulas are not in the reference sheet, so we have to try and figure out a way to remember these. The mean of a geometric distribution is just 1 over the probability of success, so 1 over p. Think back to binomial. Binomial, we multiplied, so geometric is different. We divide. I don't know if that'll help you remember this formula, but we have to remember that the mean for a geometric distribution is 1 divided by the probability of success. And the standard deviation of a geometric distribution is right here. I'm going to simplify this formula a little bit. The square root of p squared in the denominator, I can also write that as just this all over p. And the square root and the square cancel each other out, so I'm just going to write the square root of 1 minus p, or the square root of failure, divided by p. So if you can remember that we always divide by p, and then remember maybe the numerator, that will help you. We need to figure out how we're going to memorize these formulas. A couple plans on having kids until they have their first boy. Assume that sex of each child is independent of each other, and that there's an equal chance of having a boy or a girl. What is the expected number of children they will have? Remember, expected also is referring to mean. What is the mean? Well, the probability of having a boy is 0.5. So you just put that in the formula. 1 over 0.5 is 2. So the mean, or the expected value of having their first boy, is 2 children. And the standard deviation of the number of children is going to be the square root of failure, so 0.5, over the square root of success, or just over success. And that gives me 1.414. So here we just have to memorize these formulas. It's pretty straightforward. We have to figure out what p is, and that's it. P is the only variable in our equation. A second geometric distribution formula is finding the probability that it takes more than n trials to see the first success. A lot of things are backwards for geometric distribution. So for mean, we're dividing. For the number of trials. We don't have a specific number of trials. We're counting the number of trials. Here, they give me the formula for greater than. In binomial and in normal distributions, we have the less than formula that we always go off of. And then if we want the greater than, we do 1 minus. Well, here, they give us the more than, so they give us the greater than situation, and this is the probability of finding more than n trials to see the first success. You're rolling a single fair 6-sided die. What is the probability that you do not get your first 5 until after your 6th roll? So the formula again is, what is the probability that x is greater than, what's n? We're looking for the 6th roll. And that is equal to the probability of failure to the n power. So probability of failure of not getting a 5 is 5 out of 6 to the 6th power, or the nth power, which is, in this case, 6. And the answer to that is 0.3349. Some examples. So suppose you take a standard deck of 52 cards and draw cards with replacement until you get a heart. Now, hearts is a suit in the deck of cards. In the deck of cards, there's 4 suits. Ignore that there's 52. We're not going to use that. There's 4 suits. There's diamonds, clubs, hearts, and spades. So what's the probability of getting a heart? Success is 1/4. Not succeeding, or probability of failure, is 3 out of 4. What is the probability that you get a first heart on your 5th try? Well, first the question asks, is it geometric? Let's think back. For geometric distribution, we need to have success. And here, it's if we get hearts. We need to have the probability to be the same. Is the probability going to be the same here? Yeah, it's always going to be 1/4 for getting a heart. Do we have independence? Yes, once you draw a card and it's with replacement, independence is true for this case. And the last condition is x needs to be counting until success, until we reach success. So what is probability that you get a first heart on your 5th try? So we're doing the number of trials, and that is for the 5th time. So that is a geometric distribution. For this, I'm looking for the probability that x is equal to 5, that on the 5th trial, I get my first heart. Well, that means I didn't get hearts how many times? I didn't get hearts 4 times. Not getting hearts is the probability of 1 minus p, or 3/4. And I didn't get hearts 4 times, and then my last time I finally did get hearts. And the probability for this is 0.079. Using the same example, so we have still a deck of cards, and we're drawing until we get a heart. What is the probability that the first heart is on one of your first 5 tries? On one of your first 5 tries is also saying the probability that x is less than or equal to 5. Remember, I don't have a formula for less than. I have a formula for greater than, the probability that x is greater than n. And that's the probability of 1 minus p to the n power. Well, what do we always do when we want the opposite? We always do 1 minus for the probability. So we're going to do 1 minus the probability of x being greater than 5. For this, the probability that x is greater than 5, I have a formula over here. It's the probability of not getting a heart, which is 0.75, to the n power, so 5. And I'm going to do 1 minus that, because it's what I don't want. And that is 0.7627. Alright, so let's see what happens to our probability the more we draw cards. Suppose you take a standard deck of cards with replacement until you get a heart. Make a probability distribution table for x up to x equaling 5. Well, we have to think about what number are we going to start with. With binomial, we start with 0 because we can have 0 as a number of people in a set of observations or a set of test questions. I can get 0 correct. I can get 0 people that greet dogs. Here, this is a geometric distribution. So I'm talking about trials. I'm counting. Do I start with the count of 0 or am I rolling a dice on trial 0? No, there is no trial 0. You always have to start with 1. So we're going to start with 1 here. And find the probability that we get a heart on the first time. Well, that's still just 0.25. The probability of getting a heart is 0.25. Now, for x equaling 2, what this is asking is, or what is the probability that I don't get a heart on the first time, and on the second time I do get a heart? So I'm going to calculate that as not getting a heart, 0.75, times getting a heart, 0.25. And that gives me 0.1875. For x equaling 3, that's asking what's the probability that I don't get a heart on the first 2 tries, so 0.75, twice I didn't get a heart, and on the third time I finally did get a heart. And the probability for that is 0.14. Next one, 0.75, I didn't get a heart for the first 3 times, and then I finally got a heart. And that gives me a probability of 0.105. And lastly, I want the probability that the first 4 tries I didn't get hearts, and on the last one I finally did. And that gives me about 0.07 something. Do you notice something? Look at the probabilities as the trials go longer. What's happening? They're getting smaller. That's what should happen if you think about it. If I'm drawing cards, the probability of not getting a heart in the longer amount of trials should be getting smaller because I should get a heart eventually. So if I keep not getting hearts, the probability of that happening starts getting very small, and it starts getting smaller. Here is homework number 4, and then also homework number 5 is on the next page. Your test is on Tuesday. I will be going over the quizzes on Monday. You have the weekend to do your homework. Please turn it in to me on time on Tuesday. Here is homework number 5. Ignore Friday because I gave it to you before Friday. So, here's the last homework.